Have you ever noticed that a balloon acts differently depending on what's happening to it? If you put a balloon in the freezer, it will shrink. If you blow more air into the balloon, it will expand. And if you squeeze a balloon and apply more pressure to the outside, it will shrink. Now, these all might seem like completely different situations, but chemists realized something really cool. They're actually all connected. Today, we're going to look at the gas laws. But instead of memorizing a bunch of equations that seem unrelated, we're going to discover where they come from. And the secret is you already know the equation that creates all of them. The ideal gas law, PV equals nRT. This equation describes the behavior of a gas by connecting four important variables: pressure, volume, the number of moles or amount of gas particles, and the temperature in Kelvin. And then we have R. R is our gas constant. Now remember, a constant is something that doesn't change. It's like the anchor that keeps the relationship balanced. So today we're going to use this equation to build four other gas laws: Boyle's law, Charles' law, Gay-Lussac's law, and Avogadro's law. Let's start with the relationship between pressure and volume. Imagine you have a container filled with a certain quantity of gas, and that quantity of gas will not change. We also will keep it at a constant temperature. What we will do is we will decrease the volume of the container. Well, what happens to the pressure if we do this? Remember, pressure is the particles hitting the walls of the inside of the container. So the more times they hit the walls of the inside of the container, the higher the pressure. So if we decrease the volume, now those gas particles are trapped in a smaller space, hitting the walls more frequently, which means the pressure increases. So if the volume goes down, the pressure goes up. They move in opposite directions. This tells us that pressure and volume have an inverse relationship. Now let's prove it using PV equals nRT. Boyle's law only focuses on pressure and volume. That means the other variables stay the same. The amount of gas isn't changing, so N is constant. The temperature isn't changing, so T is constant. And R is always constant. So everything on the right side of the equation is constant. So P times V equals a constant. The pressure times the volume will always equal the same value. And we don't even need to know the number of particles of gas in the container or the temperature of the container. If we have a gas before and after a change, the initial pressure times the initial volume will equal the final pressure times the final volume. And we just created Boyle's law. P1 times V1 equals P2 times V2. We don't even need to know the other variables if we have a before and after situation with the pressure or volume changing. Now, when you do calculations involving this gas law, just remember to keep your pressure units the same and your volume units the same, and everything will work out. Next, let's take a look at the relationship between volume and temperature. Imagine taking a balloon outside on a cold winter day. After a while, the balloon shrinks. Why does it do that? Well, temperature tells us about the motion of the particles, and when the temperature decreases, the gas particles slow down. They don't hit the walls as often or with as much force, so the balloon takes up less space. Lower temperature gives a lower volume. Both variables are moving together. That means that the volume and temperature have a direct relationship. Now let's go back to the ideal gas law, PV equals nRT. Charles' law only focuses on volume and temperature. So what stays constant? Well, the atmospheric pressure is constant, and the amount of gas inside the balloon stays constant. And R is always constant. So let's rearrange our equation and put our two changing variables on the left-hand side and all of our constants on the right-hand side. If we do this, we get V over T equals a constant. That means that the relationship between volume and temperature will always stay the same. So we don't need to know the pressure and we don't need to know the quantity of gas in the balloon. All we need to know are before and after variables of volume and temperature. And we've just created Charles' law. Now, one important feature about Charles' law is it includes temperature, which has to be measured in kelvins. And the reason is because we need to be using an absolute temperature rather than just a degree temperature. So the absolute temperature would need to be measured in kelvins. If you don't do this, your math will not turn out. So don't forget to convert, if you have Celsius, convert it to kelvins while doing this equation. The volume units don't need to be converted. So you just need to make sure that the volume units are the same as each other. So if you use milliliters for volume 1, then milliliters needs to be used for volume 2. All right, let's move on to Gay-Lussac's law, which shows the relationship between pressure and temperature. Now we're going to think about a sealed container, and the important word here is sealed. Think of an aerosol can. The volume of it does not change. Now you've probably noticed on an aerosol can there's a warning label that says do not heat or contents under pressure. So imagine we heat this aerosol container. It's getting hotter and hotter and the particles are moving faster and faster. Well, this causes them to collide with the container walls more often and with more force. So what happens to the pressure? It increases. The temperature goes up and the pressure goes up. That's the same direction. This is a direct relationship. So we're going to build that equation. Start again with PV equals nRT. Now Gay-Lussac's law compares pressure and temperature. The volume of the container stays constant, which we know we have an aerosol can that has this constant volume, and the amount of gas in it stays constant. And we know R is always constant. So we want to put pressure and temperature together on the left-hand side, and then we want to put all of the constants on the right-hand side. So we get P over T equals a constant. So as you know, we don't need to know the quantity of gas in this container or the volume of the container. We can use the equation P1 over T1 equals P2 over T2 to compare initial and final conditions. Now remember, we're using a temperature measurement here, so everything has to be converted to kelvins, otherwise it won't work. Pressure can be any unit as long as the two units for pressure 1 and pressure 2 are the same. All right, let's move to Avogadro's law, which compares the volume and amount of a gas. So imagine you're blowing up a balloon. What are you adding to that balloon? Well, you're adding more air molecules. And as you add more particles, what happens? The balloon expands. More particles gives it more volume. Fewer particles gives it less volume. Same direction. Volume and number of moles N have a direct relationship. So back to the ideal gas law, PV equals nRT. This time we care about volume and quantity. Pressure stays constant and temperature stays constant, and R is always constant. So if we put volume and quantity on the left-hand side and everything else on the right-hand side, we get V over N equals a constant. If we want to compare initial conditions and final conditions without having to know the pressure or the temperature, we can use V1 over N1 equals V2 over N2. And we've just created Avogadro's law. So now you know the secret. You don't have to memorize 4 separate gas laws. They all come from PV equals nRT. The trick is to ask yourself 3 questions. Which 2 variables are changing? Which variables are staying constant? And do the changing variables move together or in opposite directions? If they move together, it's a direct relationship. If they move opposite each other, it's an inverse relationship. These equations are not random. They're just mathematical ways of describing how gases behave. Chemistry becomes a lot easier when we stop memorizing patterns and we start understanding where those patterns come from.